Here we are, it's the physics video lecture. Physics 107B video lecture 14. So we're talking about waveguides today. We're going to solve Maxwell's equations in, say, a straight metallic channel. That's the idea. Good for propagating a lot of power. Think microwaves through a metallic channel. You can have microwaves through this ruler here, which happens to be a hollow channel, but it would have to be metal. Okay, so the topic is guided waves. So first of all, we need some kind of channel, and we're not starting with a square channel, we're just starting with any old cross section here in X and Y. So imagine we got X and Y like this, and then we're going to propagate these waves in the Z direction, like that. And it turns out they're no longer going to be purely transverse waves. We have to have all three components. So first of all, we have a perfect conductor. This channel is a perfect conductor. The boundary conditions are now that parallel E field equals 0 at the boundary, and the perpendicular B field, B perpendicular equals 0 at the boundary. And finally, all three components are possible. So E, B have all three components, which is to say they're not generally transverse. We'll see some conditions on that later on. Good, so what do we have? We have Maxwell essentially in vacuum, and then we're going to impose the boundary conditions. That's why it's a great problem. There are boundary conditions because of the size of the thing, and then we get eigenvalues, and it's interesting. Good, so what do we have for Maxwell? Divergence vanishes for both electric and magnetic fields. Then we've got our curl of E minus dB dt, that's Faraday, and then we have curl of B equals 1 over C squared dE dt. So these four Maxwell equations are going to have, let's see if I can, they're going to have a trial solution that propagates in the direction of the axis here, okay, but is an unknown function across the cross section, which is in X and Y. So let's see here. The next thing, I want to fit everything on one board so we can stare at it. So our solutions are going to be of this form: E of X and Y, e to the I, kz minus omega t. We're going to have the same thing for the B field as well. Like I said, all three components, B of X and Y, e to the I, kx minus omega t. So we just have to, and what we're going to do is write these equations out, all six of them, and then we'll evaluate them according to this, and we'll have we'll be part way there. We'll have our differential equations partly, then we'll impose these conditions on them. So yeah, the first thing is just to write out all of these curl equations and try to fit them all on the left side here. So d dy is z minus d z minus dx dt, and same with y and z. d dz dx minus So we need the other three of these for the curl of B. And that'll be the same thing. We'll have 1 over c squared dE x dt, and the same for y and z. dx minus dx dz, 1 over c squared dy dt. Looks like we could squeeze them all in here. And dx x equals 1 over c squared ez dt. So yeah, we have all 6 of those equations. We want to evaluate them with these trial solutions here. So making sure I have all these right here. Yeah. So what we do now is the y and the x derivatives are never going to show up here, are never going to evaluate this exponential. So it's the z and t derivatives that are going to bring something out of this exponential. Otherwise, we just have to write the derivatives down. So we have, from this first equation, d dy ez, and then we have minus ik dy equals, and then minus the time derivative, you get 2 minus signs, we're just going to get I omega bx, and on through all the rest of them. And yeah, I'll just write these out now so that I have ikex minus ddx ez, I omega by ddx ey minus d dy dx is equal to I omega b sub z. And we're going to do the same thing for these 3 down here. dy bz minus ik 1 over c squared. In fact, here I can have the minus I omega over c squared dx, and on down as well, just like these 2 right here. And finally, ddx dy dx equals minus I omega over c squared ez. So we have these 6 equations, and so what we're going to do next is, you'll notice we have the dxyz. We want to get bx, by, ex, ey in terms of bz and ez. So next, express ex, ey, ex, ey terms of ez and b sub z. And I'm just going to write those down, and then we can point at these and see where the algebra comes from. That's a few steps. And we'll stack them right here and then onto the next board. So here's what we get. This will fit here. So we get, let's just do one of them first. B sub x I omega over c, the quantity squared, minus k squared times k d bz dx minus omega over c squared dez dy. So where does that algebra come from? We've got I omega bx here, okay, and d dy ez right there. So what we're substituting in is the ey from down here, okay. We substitute the ey from down here into this equation, and we're going to get the ik times bx again. So there's going to be, ik plus I omega with whatever factor is multiplied by. You have to divide by this whole thing. So you get the common factor times the bx, and then you're left with these two derivatives. This one we already had here, and this one you have right there. Okay. And that's where this comes from here. Okay. So it's just a couple steps. And let's write down all four of them, because we do need all four of them. Bx, by, they all look very similar. I over omega over c squared minus k squared, k d bz dy plus omega over c squared d. Easy, yes. X. And I'll put the other two right underneath here. So those bx and by, ex and ey, we have omega over c squared minus k squared, k d bz dx plus omega d bz dy, and finally e sub y omega over c minus k squared minus omega. Yeah, these cross product things are going to come into play right in a moment here. D bz dx. Okay, so what we notice here we're going to have these cross terms here. What we notice is that these fields, bx, by, ex, ey, all depend on bz and ez. That's a z there, looks kind of like a plus. B and e sub z, as noted here, that means if we can find these two, e sub z and b sub z, then we'll just be able to get the other four components by differentiation. Okay? So we're going to have to continue with this process in order to get differential equations for e sub z and b sub z. That's our goal, and I just erased the other two Maxwell equations, but we're going to use the divergence equation on these results now. So we already have this here. We'll use the divergence equation in order to get the differential equations that we're looking for. So we'll use this side of the board for that. So next, well, I should put that as a note here, just for the record. Note that given E sub z and B sub z, if we can solve for those, then EX, EY, BX, BY are obtainable by differentiation. So we've already accomplished something. Differentiation. Okay, so what comes next is divergence of E equals 0 and divergence of B equals 0. So for the divergence of E, for starters here, we would have dEx dx plus dEy dy ez is equal to 0. And let's see, we have for E sub x, we would have I omega over c squared minus k squared. We're taking the derivative with respect to x, so we would have k d squared ez dx squared plus omega d squared dx dy of b sub z. Now I'm going to stack these. So now dEy dy would be I omega over c squared minus k squared. And the same thing here, E sub y with respect to y, k d squared E sub z dx squared minus omega d squared dy dx. Here we have the dx there, b sub z. And then my third one, ez dz equals 0. But that one, do I have the ansatz up there still? I do. That one, we're up here again, and we have the ikez plus ikez equals 0. Okay, that looks not so good, but you'll notice when we add these up, these cross terms go away, and we've got this factor in front, k d squared x squared plus d squared. This should have been y. Yes, y squared. These cross terms vanish. Let's see how much room it takes to write this down here. Yeah. So from this, this right here, we get d squared dx squared plus d squared dy squared plus omega over c squared minus k squared, all operating on E sub z is equal to 0. Okay. The ik is common there. We just cross multiply over and it's already done. Okay. So we have this, put it in a red box, and we'll have the identical equation for B sub z. Okay, because these things look exactly the same. Actually, they don't look exactly the same. Make sure that works. So when you do the divergence for B, cross terms go away. Got the IK. Yeah, that's good. So, same thing for B. B squared, x squared, d squared, y squared, omega over c, k squared, operating on b sub z is equal to 0. Okay, so there was the result that we're looking for. So now what we have left is to actually set these up in a concrete case, solve, and we're going to see we only have to solve for one of these two, impose the boundary conditions, and then everything else will follow. And then, like I said, if we needed the other components, we'd have these equations right here to get them. Okay. And the boundary conditions, actually we're going to use these, but I'm going to have to erase them. These also will count, will help us in terms of the boundary conditions as well. So these we're going to refer to, although I'm going to erase them. Let's see one more thing here. Yeah, that's good. Okay, so now we're going to apply this to a rectangular channel. This is where the shape of the channel definitely does come into play if we actually want to solve these equations. So for a rectangular channel, we'll be using our sines and cosines. Other shapes of channels will use other special functions. Okay? So we'll do the rectangular channel, and oh, I see I have a couple of definitions first. Okay, so we have the differential equation for EZ and B sub z. So we have equations for both E sub z and B sub z. Now, there are three possibilities here. If E sub z is equal to 0, E sub z is equal to 0, E sub z and B sub z are equal to 0. These are called transverse electric and magnetic, because if both components are 0, then you have the original transverse wave. And magnetic, or TEM. But you can see from our equations here, are they still up there? I just erased them. You're actually not going to be able to support those waves. You're going to have all your components vanish identically unless you have a coaxial type of situation that we didn't set up yet. So that one has to be treated has to be treated separately. We'll do it either the transverse electric or the transverse electric or the transverse magnetic. Verse electric. Okay. So transverse electric and magnetic aren't actually supported in an open channel. It has to be a coaxial. Channel. That's interesting in its own right. But yeah, so we're going to treat one of these two right here. And the one we're going to treat is the transverse electric wave. So transverse electric in a rectangular channel. Rectangular channel. So I'll just have to draw it and label it. And we're going to take X and Y axes like we had before, but now we've got a rectangular channel. So we go to A in the X direction, we go to B in the Y direction, and then this is just a channel in the Z direction. There's your channel, rectangular channel. So, because we're taking the transverse electric, E sub Z is equal to 0, and we're looking at our equation for B. Looking at this equation for B sub Z. So now what we have to do is solve this with the boundary conditions. Let's free up some space. That's our equation. And make sure we get everything here. So E sub Z is equal to 0. And we'll just put this up in the corner and we ought to be able to fit this on one board. Omega over C squared minus K squared. E sub Z is equal to 0. So we're going to do the separation of variables. So separation will have the X and Y component. It's just going to be a function of X times another function of Y. We'll just name them uppercase X and Y. And go into the differential equation. Yeah. I've written this for a while, but this was X and Y. Remember, the Z was just the exponential, okay? And we've gotten rid of that a long time ago. So yeah, this is definitely what we're just solving for. So we've got two derivatives, X, two derivatives in Y. We do the standard. And then we'll have Y plus D squared Y squared. And we'll have the capital X plus omega over C squared minus k squared, and that will be times the x and the y is equal to 0. We divide the whole thing by xy, uppercase, and then all three of these expressions, right, the y cancels, all three of these expressions, x cancels, both of them cancel, are equal to constants. Okay. So this one, I'll do is different color. This one, we have, and then these two we have minus kx squared. That doesn't work. Minus case of x squared minus case of y squared, and minus case of x squared minus case of y squared plus this here is equal to 0. So now what do we have? Yeah, let's write this out. So minus kx squared, ky squared plus omega over c is equal to 0. Very good. And d squared x dx squared over x is minus kx squared. So that's your sine again, sine and cosine. So what do we have here? d squared x, d lowercase x squared equals minus kx squared x. So we have x equals a cos kxx plus b sine kxx. We're going to have the same thing for y. Same type of expression, different constants. Okay. Very good. So we're going to hold on to this. And now we have to impose the boundary conditions. And those aren't all on the board right now. Dx equals 0 at x equals 0, x equals a. db z dx equals 0 at x equals 0, x equals a. This is from one of those lists of equations that I had. Yeah. This isn't directly visible from the boundary condition here. You'll find it in one of those combinations of equations there. In fact, let me dig that out and make sure we see it here. Yeah. I'll write here from I k dx minus d dx dz equals minus I omega ey over c squared. The reason being is You have this already vanishing, you have EY vanishing, okay? And therefore this one itself has to also vanish. So that's the one we're going to impose on our solution up here. So here we go. Here, I'm gonna go ahead and erase this. Well, I'll leave that picture up there. Old x dx is minus kxa sine kxx plus k x b cos kxx, and that's supposed to vanish at x equals 0 and at x equals a. Okay. So we're going to have to let b equal 0. Okay. Equal 0, and then we're left with sine kxa, or actually I can just say kxa is equal to m times pi. Okay. All the integers. And then for the same argument for b, same argument for y, kyb n times pi, and we can now put all these together. B0, both times we keep the cosine. That was the derivative, so we keep the cosine m pi x over a cosine n pi y over b. So there's our solution. The last thing we have to do now is evaluate this expression up here, and that'll have our dispersion. Okay, so I'm going to leave this picture up here and this function. So yeah, we have our kx squared equals pi squared m squared over a squared, ky squared pi squared n squared over b squared. So we're going to plug that all in and then take a look at what we've obtained here. Once again, that's ky squared minus k squared is equal to 0. So we're going to solve for k. We're going to have the square root of minus k sulfur K, omega over C squared minus KX squared minus KY squared, which were these things here. Minus pi squared n squared over b squared. Okay. So there's our result. Let's clean this up a bit. Let's clean this up a bit. We'll pull out the factor of pi here, and then we can see a little better. Plus n squared over b squared. So for any given frequency, there's actually, that's a minus. There's actually going to be a cutoff where this part here is greater than omega over c squared. Okay. So you don't have an infinite range of these for any given frequency that you're sending down. And the question is, what happens to those modes? Because if this thing becomes imaginary, actually imaginary numbers are not forbidden in what we're doing here. If this expression becomes imaginary, though, you go back into our original expression, you see you're going to get damped waves. Okay. So write a note. For your large m and n, K becomes imaginary, and then just as we had the other day, you have damping. So there's one more thing we could do with this, and that is check the speed of these waves. The phase velocity and the group velocity. And that's an interesting exercise, okay? So let me just write this down and I'll let you guys go ahead and leave room in your notes and do that. You have V phase is just omega over K, and you find an interesting result, it's greater than C, okay? But the group velocity, which is d omega dk, and you're, well, you don't have omega of k here, do you? Here's what you do. You say that's 1 over dk d omega, and what you'll find there is that that is less than c, okay? And that's really pretty straightforward, but it's an interesting result. We've got a higher than speed of light phase velocity. But as far as information traveling down that channel, information, power, whatever, that is always speed of light or less, and that'll satisfy that. So I think that's what we have from this chapter. You know, I may talk about the coaxial modes. So TEM in a coaxial channel. But we'll save that for next time. Good, we'll see you then.